All right, let's look at problems from 11.8. I feel like 11.8 is kind of concept heavy. The actual mechanics from 11.8, there's not a lot. Maybe it's kind of technical, but really there's only one thing we're doing in 11.8, finding interval of convergence, radius of convergence. I guess that's really two things, but radius of convergence doesn't even count in my opinion. Really, the grunt work is all coming from finding that interval of convergence. So let's try a problem. Number 3 from the textbook, section 11.8. Find the radius of convergence for this series. Okay. So this power series. 99% of the time, we're going to start by doing a ratio test, which means we need to find an plus 1 over an. Okay. So let's find that. Simplify. Okay. And we want to find the x's that make this limit less than 1. Well, first of all, absolute value gets rid of the negative, right? Okay. And we want the limit of an plus 1 over an to be less than 1, meaning we want the limit of n plus 1 over n times x to be less than 1. Okay. So really what I need to do is, and I shouldn't have dropped the absolute value, right? I got absolute value there. So I want this inequality. Okay. I want n plus 1 over n times x to be less than 1. I need to solve this inequality. Okay. Well, the limit of this thing is 1, right? So I can ignore that. Okay. So really what I need is I need an absolute value of x to be less than 1. So I need to solve this inequality. So the only thing I do is I drop the absolute value bars and I got x greater than -1, less than +1. Okay. So that's my my first piece of this problem. I know my series is going to be converging inside here. Now I need to test these endpoints. Okay, do I include the endpoints or not? How do I test the endpoints? I'm going to take -1. That's my first endpoint. I'm going to plug it into that series for x. Okay, so when I plug in -1, I have -1 to the n times -1 to the n. I'm plugging -1 in for x. Right? So let's simplify this. Okay. That's always positive, right? -1 to the power 2n, okay? That's always positive. So that series is really just the series n. Just the series converge or diverge. Well, definitely diverges. Now let's try plugging in x equals 1, positive 1. Okay, so this was x equals -1, right? Let's try plugging in x equals 1. When I plug in x equals 1, get this. I simplified this series and it simplifies to what? -1 to the n times n, right? 1 to the power n, that's always just 1. So I got this series. Does that converge or diverge? Well, that diverges too. So I don't want to include x equals 1 either. I don't want to include either endpoint. So my interval of convergence looks like this. It's just the stuff in the middle. I'm not including the endpoint. Now I just need to write that in interval notation. So that's my interval of convergence. All right, to find the radius of convergence, I just take the length of this and divide by 2. Well, this is 2 units long. I divide by 2, so that gives me 1. All right, let's try another problem. Number 7 is an interesting one, and that's going to be a series, a power series we'll become very familiar with. So remember, 0 factorial is equal to 1. So starting our series at 0 doesn't give us a problem there. Okay. So again, I'm doing ratio test. Then I'm simplifying. Remember how to simplify n factorial over n plus 1 factorial. I want this limit to be less than 1. Okay. For what x's is this limit less than 1? Okay. And the interesting thing here is that no matter what x I plug in, the limit's eventually going to be less than 1. So let's say I plug in x equals 100 billion. As n goes to infinity, I'm eventually going to be dividing by a number much bigger than 100 billion. Okay, so no matter what x I plug in, the limit's equal to 0. Another way to kind of to think about this is look at these pieces individually. The limit of the n stuff, okay, that limit is equal to 0. And so no matter what this x is, x times that limit is going to equal 0, which is less than 1. So my ratio test is always going to tell me that my series is absolutely convergent no matter what x. So how do I write this interval of convergence? Well, that would be negative infinity to infinity. Okay. How do I write my radius of convergence? Well, what's half this distance? Well, that's still infinity. Okay, let's move on to the WebAssign homework, see if there's any hard problems on there we want to review. Problems 1 and 2, those are basic just inequalities. Okay, maybe they're challenging, but that skill set's necessary for 11.8. I won't review that. You guys can review that on your own. Number 3, fairly basic, radius of convergence. Number 4 also looks fairly basic. 5. I think 6 is interesting, but let's go ahead. I think 7, 6 and 7 are pretty, the result is pretty similar. Maybe series are very different, but the result is very similar. So let's just go to number 7. I like number 7. So we're starting with this series. And we want to find radius and interval of convergence. Okay. I always start by finding the interval of convergence, and then I find my radius of convergence. Okay. So let's find interval of convergence. So I do an plus 1, I do my ratio test, an plus 1 over an. I don't know why I did that. I wrote it nasty. And then I'm dividing by the reciprocal, or excuse me, multiplying by the reciprocal. Okay, now I'm simplifying. Let's go ahead and group the similar stuff with similar stuff. Okay, so I've grouped. Now let's simplify. Now I want this absolute, I want the limit of this thing to be less than 1, right? Limit of this piece is equal to 1. So I need to make sure that this stuff, the limit of this stuff is less than 1, or that this stuff is, the value of this stuff is less than 1. So what I need is, I need this inequality. So let's solve this inequality, and let's just go ahead and rewrite it here. Okay, I want to solve this inequality. So I drop the absolute value bars. And I have this. I multiply both sides by 2 to get rid of that 1/2 in the middle. I subtract 5 from both sides to get x by itself. And I have this inequality. So I'm starting off with this. My series definitely converges in here. Now I need to test the endpoints, right? So let's plug in x equals -7 to my original series. Oh, that's not my original series. This is my original series. Okay, so I plug in -7 to this, and what do I get? I plug in -7, that becomes -2 to the n, right? I simplify 2 to the n, let's say -2 to the n divided by 2 to the n. This series becomes -1 to the n times n. We saw an example of this earlier. We know this is going to be a divergent series. So I don't want to include x equals -7. Now let's try x equals, what is it, -3. Again, I'm plugging that into here. When I plug in x equals -3, I get what? Positive 2 to the n. So I got 2 to the n, or let's say I got 2 to the n divided by 2 to the n. So I'm just left with the series n. Again, that series diverges. So I don't want to include x equals -3 either. So my series just converges inside. I don't include the endpoints. Okay. So how do I write this in interval notation? -7, -3, parentheses on both. That's my interval of convergence. What's the radius? I take this length. What's that length? That's 4. I divide by 2, and I end up with a radius of convergence equal to 2. Okay. 8. 8 is an interesting example. Number 8, so I said like 99% of the time we do ratio tests, right? We've done a lot of ratio tests. Number 8 looks like one of the rare examples where we could do root test. Okay, so let's number 8 real quick. Really how we're finding these interval of convergence is finding the x's that make our series absolutely convergent. So remember, there's 2 ways to show absolute, or two nice tests for absolute convergence. We got ratio test and root test. And if we, to be technical, there's 3 ways. We could do it by definition as well, but let's stick with ratio test, root test. We've been using ratio test for almost everything, right? All these problems up here are all ratio tests. But now I have a problem where I have everything's to a power n. So that makes me think root test. Okay, so let's try and use root test to find the x's that make everything less than 1. Okay, so I do nth root of an, absolute value of an. Okay, so that would be, for this series, that would be nth root of x minus 3 to the n over n to the n. All right, that might look a little confusing, but note that the key idea here is that x minus 3 to the n over n to the n, that's the same thing as x minus 3 over n to the power n. Okay. So really what I'm doing is nth root of x minus 3 over n to the n. Okay, absolute value bars there. All right, so the nth root and the n cancel, and I'm left with x minus 3 absolute value over n. And I want this to be less than 1. Okay, when is this less than 1? Well, it doesn't matter what x I plug in, right? And eventually n is going to be so big that the limit's going to be 0. Another way to think about this is I could rewrite this as x minus 3 times 1 over n. The limit of this piece is 0, and then x minus 3 times 0 is always 0. So that's always less than 1. So this is a series that converges everywhere, converges for all x. So interval of convergence, negative infinity to infinity. Radius of convergence, infinity. Number 9 looks straightforward. A little hint, okay, or a little tip. Sometimes, so we've seen a lot of problems where the interval of convergence was like a finite interval, maybe -2 to 5. And we've seen some examples where it was that, every all x's, that infinite interval. But remember, there's a third possibility, right, where our series just converges at a single number, right? So how do we write a single number in interval notation? Like, let's say our series only converges at 7. How do we write just the number 7 in interval notation? It's the braces 7. Okay, it's not parentheses 7. It's not brackets 7. It's this thing, braces. The curly, curly brackets, they're often called. I call them braces. I don't even know if that's correct. I think it is. So that's a tip there. Okay. And in fact, let's just go ahead and do problem 9. I think once we do problem 9, we'll kind of have seen all the possibilities. Okay, so problem 9 from the homework. We're trying to find radius of convergence, interval of convergence for this series, n factorial 9x minus 1 to the power n. So again, I'm going to go back to using ratio tests. Okay, so I do a ratio test. I simplify. I get this thing, right? So for what x's is this limit less than 1? Is it ever possible? Well, let's see. If I plug in x equals 1 over 9, okay, then I would have n plus 1 times 1 minus 1, n plus 1 times 0. So that's 0. So the limit of that is 0. Okay, so the limit's 0 when x equals 1 over 9. What if x is anything else? If x is anything else, then I'm going to have n plus 1 times 9x minus 1. It doesn't matter what x is. If it's not equal to 1 over 9, okay, this is going to be some, some number. And then the limit of this piece is equal to infinity. So unless this is 0, okay, if this is anything other than 0, the limit of the whole thing is going to go to infinity. It's going to diverge, right? So the limit will be greater than 1 if this is anything other than x equals 1 over 9. All right, so what does that mean? That means our series only converges at x equals 1 over 9. How do I write that in interval notation? As I said before, the braces. So that's my interval of convergence. What's my radius of convergence? Well, there's no radius, right? It's just a single point. So let's say radius of convergence is equal to 0. Okay. So now I think we've seen all possibilities for these, 3 different cases of intervals, right? We've seen the finite interval, the single point, and the infinite interval. So that covers all the bases. Let's see, let's look at the remaining problems. Number 10 looks a little different than you're used to, but should be doable. Yeah, I think you guys can handle that. Number 11, definitely. Let's see, would that be ratio test or root test? No, I'd still stick with ratio test for number 11. 12, that looks doable as well. And then it looks like 13 begins some review. Okay, so that'll be all for this section. Good luck.